Recording. So on your canvas, I have uploaded a number of documents. So for example, lecture 14 and lecture 15 up to last week, we had examples on diodes, the introduction to diodes, as well as some basic understanding of diodes from device physics. I haven't gone through the understanding of diodes from device physics. This is optional. So this is something that I'll put as a self-study. If you're interested in learning more about diodes, please go through that document. For today's lecture, I have also put a few self-studies on BJTs. I'll first finish the discussions on diodes, and then we'll look at BJT intros as well. But I have, because diodes and BJTs are very much interlinked with each other, what I have done is I have put the recorded lecture from last year on BJTs, even though BJTs were covered later in the course. But please go through some of those lectures as self-study. And once we cover MOSFETs, we'll come back to BJTs once again. Okay. Because some of the ideas that we learn in MOSFETs will be very much applicable to BJTs as well. However, you'll see that in terms of the structure, the diode and BJT are very similar. That's why I have put some of these discussions over here if you are interested. But we'll again go back to these two lectures, the BJT basics as well as BJT analysis later on during the course. So no worries if you're not into BJTs right now. But if you're interested, please go through the recorded lectures. And then over the next three lectures, we'll discuss this intro to MOSFETs and proof of the MOSFET IV characteristics. You already looked at the diodes IV characteristics. That's the current versus voltage for the diode. And you know that if the diode voltage is on the x-axis and if the diode current is represented on the y-axis, you know that it looks like this, right? And then there's a reverse saturation region on the left side as well. We'll take a look at how this curve looks like for MOSFETs over these next three lectures in this week, and we'll also try to prove those equations. All right, so with that, let's start with today's lecture. All right. So over the last two lectures, we have looked into different regions of operation for the diode. We have looked into no bias region, forward bias region, and reverse bias region. So, for the diode to conduct, you need to have the diode in the forward bias region. That is, you apply a positive voltage to the diode. So you apply a positive voltage to the P side and a negative voltage to the inside, or the lower voltage to the inside. That's what is meant by forward biasing a diode. Reverse biasing a diode is just the opposite. That you apply the negative voltage to the P side, the positive side of the diode, but apply the negative voltage or apply the positive voltage to the N or the negative side of the diode. So that's reverse biasing. And you know that in the reverse bias region, there will only be a small amount of leakage current. That's because there are minority carriers in the depletion region that you have for the diode. We have looked into depletion region as well. So if you look at this figure on the bottom left, if you have a reverse bias, then the width of the depletion region increases. And if you have a forward bias diode, the width of the depletion region decreases. It's kind of like how you have a bridge, and then part of that bridge is broken. So the electrons or the holes have to jump through that broken part of the bridge. If you have a reverse bias diode, the broken part is larger. If you have a forward bias diode, the broken part is smaller. And then with that, we learned about some of the resistances that you define for diodes. So average AC resistance, dynamic AC resistance. We also proved that the dynamic AC resistance is 26 millivolt divided by ID. And that comes from this equation, this particular, okay, let me go full screen. So what you see on the right-hand side is basically the calculation of why your AC resistance is 26 millivolt over ID. Because it's eta times Vt, and Vt is the thermal voltage, which is equal to 26 millivolt, Kt over Q. K is the Boltzmann constant, T is the temperature, Q is the charge of an electron. So if your Vt is Kt over Q, you can calculate that to be 26 millivolt. If your eta, that is the non-ideality factor for the diode, that's an empirical factor that's used to match the theory with what you actually see in measurement. So you already have bought a diode for this class for the labs, and if you measure the IV characteristic, this characteristic in the lab, you will see that it does not exactly match with that exponential theory. So this particular equation that you have over here, in measurement, you may not exactly match it if you're considering VD over VT. So that's the reason why this eta factor or the non-ideality factor is considered. But if you consider that non-ideality factor to be equal to 1, then your average AC resistance or dynamic AC resistance is 26 millivolt divided by ID. All right. So we also started looking into diode applications. We looked into the load line. We looked into forward bias diodes as well as reverse bias diodes, and solved one or two problems, I guess, in the last lecture. Yeah, one problem over here. And then we also looked into half-wave rectification. That's one application of diode-based circuit. So if you have a AC voltage or AC current, can you create a DC out of it? The answer is yes. And the solution to that is by using a half-wave rectifier, which is a diode-based circuit. You already know the diode only conducts in one direction, and you can apply that property, you can use that property to make sure that if there is a sine wave, AC sine wave at the input with an average value of 0, so let's say your average DC potential is 0. Then on the output side, as the diode is shorted, as it is forward bias, that is, you are interested only in the positive half cycle. When the diode is shorted, you get the positive half cycle at the output. When the diode is open, you do not get anything at the output because you have an open circuit in between. Okay, and the output is taken across this resistance over here on the right-hand side. So the average value of the sine wave with a DC value of 0 is equal to 0, right? So if your average value, if your DC or the common mode is 0 for the sine wave, the average value of the sine wave is 0. However, the average value of the half sine wave is not 0. And we proved this in the last lecture, that the average value of the half sine wave is going to be 0.318 times Vm, where Vm is the basically the amplitude of the sine wave in one direction. So if this is Vm, then the average value of this half sine wave rectified waveform is equal to 0.318 times Vm, which we proved in the previous lecture. And this just comes from the fact that you can have that integration in two parts, one from 0 to t over 2, that's basically half of the cycle, and then t over 2 to t, that's the second half of the cycle, where the value of the signal is equal to 0. Okay? And if you do this math, once you do the integration, you'll eventually end up with this 0.318 times Vm. That's the average value of the half-wave sine rectified signal. Okay? And this, because this is non-zero, so you basically have a DC signal now, which is, so you, to have a, now there's one thing that I did not talk about, that what you have after the half-wave rectification is just this half sine wave. So you have this part and you have this part. Now, how do you average this half dome-like signal? Yeah, you just create an averaging circuit or a low-pass filter. A low-pass filter is an averaging circuit. So what a low-pass filter looks like is basically a resistance, then a capacitance to ground. Okay. So if you have a low-pass filter, then what would happen is that there is an AC component for this half sine wave rectified signal, and there are DC components. You already found out the value of the DC component is 0.318 times Vm. If you take an FFT, or let's say Laplace transform, and then represent this signal in the, let's say x-axis is frequency, and y-axis is the frequency domain amplitude. In that case, you'll see at zero frequency, there would be a component. And that zero frequency component is basically the average value of the signal, because the average value has no frequency, right? And that average value is already, you found that out to be 0.318 times Vm. And then there could be components at higher frequencies. right? There could be multiple components at higher frequencies. Now, if you low pass filter this, let's say you just take the DC component, then you only have the average. And then let's say you cut off all other frequencies, any other frequency that is present here. So basically the fundamental mode frequency of the sine wave was, let's say, at this point. If you create a low pass filter for which you have the cutoff frequency much before the fundamental frequency of the sine wave, then what you are left with is only this DC signal, right? You get rid of any other high frequency. You want to filter out only the DC signal. And that you can do with this very simple RC circuit. Only thing that you need to keep in mind that the omega p, the pole frequency for this RC circuit, is equal to 1 upon RC. And you need to make sure that omega p, this pole frequency, has to be much lower than the fundamental frequency of the sine wave. And that is the easiest way that you can average the half sine wave. And in that case, you'll get a non-zero value, which is this 0.318 times Vm, which is already present as your DC component. All right. Now, one other important concept that we did not talk about related to diodes is there is a peak inverse voltage or a peak reverse voltage. What does that mean? That when you have this diode forward biased for half of the cycle, you also know that it's reverse biased for the other half, right? When you are using this for half wave rectification, you know that the diode is reverse biased for the other half cycle. Now, it is important that the reverse breakdown voltage of the diode should be high enough to withstand the peak. Otherwise, the diode might be damaged by it may not be fully damaged, but it may be damaged by some amount, right? So it may not have the same behavior when you go back to the forward bias condition. So you need to make sure that the peak inverse voltage or the peak reverse voltage, this will be a term that we'll find in the diode data sheet. So if you look into the data sheet, it will give you the peak reverse voltage. And you need to make sure that the peak reverse voltage is higher than what you are subjecting the diode to. The diode is seeing a maximum peak reverse voltage of Vm. So the peak inverse voltage that the diode can withstand has to be higher than that. So you just need to make sure you check that in the data sheet when you're using a diode. Now the question is, can we do a full wave rectification? We already saw that we can do a half wave rectification, and that's pretty cool because you can create DC signal out of AC. When you, for example, if you want to see, if you use generators or inverters to, let's say, generate power from your AC source, right? So you can have an energy harvester. So the generator or the inverter, what it does is that it creates an AC signal from DC, right? But if you want to create DC signal from AC, that is, let's say you're receiving some amount of power on your cell phone and you want to convert that to energy. You want to store that energy in a capacitor. Because you're receiving a sine wave, the average value is 0, right? But if you receive a sine wave and then half wave rectify it or full wave rectify it, then you'll get a non-zero DC voltage and you can store that DC voltage in a battery. So that's how, for example, wireless chargers work. Now, this rectification can be done using a full wave rectifier circuit as well, that you have half the cycle over here. The other half cycle, if you can somehow flip, if you can somehow mirror this part and then put it over here, then the full wave VDC, the full wave rectified voltage, average voltage, is going to be double of the half wave rectified voltage. For the half wave rectification, we already found that the average value is 0.318 times Vm. For the full wave, it's going to be double of that. So 0.636 times Vm. So that's basically Vm divided by pi and twice Vm divided by pi. Now, how do we achieve that? How do you do a full wave rectification? One way to do the full wave rectification, the simplest way, is to use something called a bridge rectifier. And in this case, you have to use 4 different diodes. Okay? Now, how does this circuit work? Let's say you have the positive half cycle over here. And this input voltage, Vi, it is applied between these 2 terminals for the bridge rectifier. So as you apply the positive half cycle, your signal voltage is positive. So only the diodes that are forward biased with a positive voltage, only those diodes will conduct. So if this point is positive and this point is negative, which diodes are going to conduct? Of course, the ones that are forward biased. So you're going to take this path, that current will go through this resistance and then take this diode to reach the negative terminal. Okay. The other two diodes are reverse bias already according to the way they are connected. So the other two diodes cannot conduct current. On the other hand, let me change the color. Let's say I use blue. Now let's say in the negative half cycle, that is when you are here. Okay. This is positive and that becomes negative, right? The polarity just gets flipped. It is switched. So your bottom terminal is now positive and the top terminal is negative. How would the current flow? In that case, the current will flow in. It will flow through the diode D4. It will flow through the resistance R and then flow through the diode D1. So this will be the flow of the current. So the flow of the current through the resistor is always going to be from right to left, right? It's right to left in this case, and it was right to left in the previous scenario as well. In the previous scenario as well, it was flowing from right to left through the resistor. So even though you have two different half cycles with two different polarities, the current that is flowing through the resistor is in the same direction, right? So you have created a circuit where for both the polarities, for both the half cycle, you have currents going through the same direction. So you have voltage developed in the same direction. And that's why if you look at the voltage across the resistor with a positive terminal on the right side and the negative terminal on the left side, you'll see an average voltage which looks like this. Of course, this assumes that the diode is ideal and the diode itself does not have any drop. Right? So we already saw in the previous lecture that the diode, if it is a silicon diode, it can have a 0.7 volt drop because you need that much amount of voltage to turn on the diode in the first place. The threshold voltage of the diode is 0.7 volts. What that means is that you need a particular amount of positive voltage to turn on the diode. So this could be 0.7. Now, in this example, we are assuming that the diode has zero threshold voltage, that the diode turns on as soon as it sees a positive voltage slightly higher than zero, which will not be true in the real scenario. But let's just assume an ideal diode for now. Okay. So that's how the bridge rectifier works. Okay. Question.
So in our hardware, of course, is 60 hertz. But say if you had like a really high frequency AC signal, would this still like rectify it, or would there be more issues?
That's a great question. That the question is, for 60 hertz or for lower frequencies, we know that this circuit will work, but would there be issues in higher frequencies? That depends on how high of a frequency that this diode can support. The diode will not let any frequency pass through it. Right? So there would be just like you saw that the op-amp has a low-pass filter kind of response. So any circuit in general has a low-pass kind of behavior because you have a finite bandwidth. You cannot really get terahertz signal through a diode, right? So it will be some kilohertz to megahertz to tens of megahertz. After that, you'll see that the diode does not even work. And in that case, you'll not see this response from the diode. So depending on the bandwidth that the diode supports, you can use that for AC rectification. Yeah. Question.
Can you just approximate a very high frequency signal as DC?
Can you approximate a very high frequency signal as DC? So if it is a single frequency, so think about it, that if you're talking about, let's say your frequency is on the x-axis and signal amplitude on the y-axis. So what you're saying is a very high frequency. So let's say over here, that is not DC, right? DC is where you have frequency f equal to 0, right?
Yeah.
So a very high frequency signal, if it does not have any DC component and you do a low pass filtering, you'll just get 0, right? So a sine wave, it does not matter whether it's a low frequency or a high frequency. The average value of a sine wave is 0. So there's no DC component, whether it's a low frequency sine wave or a high frequency sine wave. Only if you have a DC component, or only if you, let's say, create a half wave rectified signal or a full wave rectified signal, then you start seeing a DC. That is the average value of the rectified signal, right? Okay. Any other questions? All right, so let's move forward. Now, in the previous case, what you saw was an interesting circuit. It is called a bridge rectifier because, again, think about it that, let's say the resistor is acting as a bridge between these two terminals. Okay. And the whatever you do, the current always flows through that bridge. Right? That's the reason why it's called a bridge rectifier. What is the problem? What is the problem in case of this bridge rectifier is that the signal flows through two diodes. So if this terminal, the top terminal is positive and the bottom terminal is negative, the signal flows through D2, then from right to left through the resistor, and then through D3. So it flows through two diodes. Again, if the bottom terminal is positive and the top terminal is negative, the signal first flows through D4, then through R, through this resistance from right to left, and then through D1. Right? So the signal always flows through two diodes. And in a realistic scenario, there would always be a drop from each of those diodes. So there would be a 0.7 volt drop from the first diode, a 0.7 volt drop from the second diode. So you lose some amount of the signal. How would it look like? Think about the first half sine wave. Until and unless the voltage reaches 0.7 volt, let's say my 0.7 volt is here. Right? So 0.7 volt is a positive 0.7 volt, right? So my 0.7 volt is here. So until and unless my voltage reaches 0.7 volt, I do not see any kind of conduction through the first diode. So the first diode will only pass this part of the signal. It will not pass the negative half cycle. It will also not pass anything in the positive half cycle that is below 0.7 volts. Similarly, the second diode will also have a threshold voltage of 0.7. So the total amount of threshold voltage that you need to overcome is, let's say, 1.4 volts. So let's say this point is 1.4 volts. So anything below 1.4 volts will not be conducted. So only thing that you see being conducted is this, right? The tip of the positive half cycle of the sine wave. Nothing else will be conducted through the diodes because the diode does not even turn on. Diode turns on only after it sees a positive voltage, threshold voltage of 0.7 volts. Questions? So I'll not say it's clipping. Clipping is opposite. So I'll show some examples of clipping as well. So what you're seeing is that this entire bottom part, what does clipping look like? That if you had a sine wave like this, and let's say the top part is getting clipped, so you're not seeing the top part or the bottom part, that is clipping, right? So in that case, instead of a sine wave, you see a clipped sine wave that may look like this. Okay, that is clipping. What you're seeing in this case is only the top part, only this portion of the sine wave. So I'll not call this clipping. It is that you're not seeing the full half cycle, you're seeing only a part of it. Yeah. So if there are two diodes, you're seeing two diode drops. Is there a way to do the full wave rectification with only one diode? In that case, you'll probably see only the drop from only one diode, and then the performance will be better. Okay. So this is called a center tap transformer based rectifier. So you already may have heard about transformers, where you transform, let's say, the voltage of current from the primary side of the coil to the secondary side of the coil. Let's say you have this as the primary side of the coil, then there's a magnetic core. And let's say that magnetic core makes sure that from the primary to secondary, you have a 1:2 voltage transformation, which means if the input voltage here is VI, at the secondary side, you'll create twice VI amount of voltage. Of course, you cannot create more power because this is a passive circuit. So if your voltage becomes double, your current becomes half, even in the ideal scenario, if there is no magnetic core loss in the transformer. So current will become half, but the voltage will become double. But in this case, let's say you're only interested in the voltage, right? So you have 2 times VI in the secondary side. What does center tap transformer mean? That on the secondary side, you have 3 terminals. Of course, you have a top terminal and a bottom terminal, but you also have a middle terminal, a center terminal, which is used as a reference. So you can think of it as something similar to your ground in a circuit, in an analog circuit, that everything will be referenced with respect to the center tapped terminal, which means that you have a VI voltage on the top half. So between this and this, you have a VI voltage. Between this and the center, you have another VI voltage. So everything is tapped, which are reference with respect to the center tap, but you have a VI voltage on the top half and you have another VI voltage on the bottom half. Yeah. Questions?
So the last rectifier is like one branch of the rectifier is on at once. So because it's a center tapped, the top half is always like 5 volts, and the bottom half is always like minus 5 volts because it's tapping in the middle. So are both diodes in this rectifier on at the same time?
No, that's a good question. So both diodes in this rectifier are not on at the same time. How it will work is that when you have the positive half cycle, you have, let's say, the positive input voltage here and the negative input here. So you'll create a 1:2 ratio of the voltages. So of course you'll have twice VI between the top and the bottom, right? So the twice VI will always be there between the top and the bottom. However, so what that will mean is that the top diode will conduct, and then you'll see current flow in this direction. How for the negative half cycle, this will be positive and this one will be negative, and still you'll get a twice VI amount of voltage on the secondary side. Okay. But the current flows in a way that this center tap, so that acts as a reference. So you see the current flowing in this direction for the negative half cycle. So now again you see that through the resistor you always have the current flow from right to left. So the resistor still creates this current flow from right to left, and that if you have only one diode in the path, assuming that the transformer is now ideal, the diode drop is 0.7 volts, you have only one diode's drop. So this is a better scenario than the previous one where you had two diode drops. But of course, in a realistic scenario, you might argue that the transformer may also has a loss, right? Now, if the loss in the transformer, it depends whether the loss in the transformer is more or less than the diode. That will help you take the decision whether in a real scenario you want to create a bridge-based full wave rectifier or a center tap transformer-based full wave rectifier. All right. So this is basically the summary of those rectifier circuits. That for the half wave rectifier, you have 0.318 times Vm or Vm divided by pi as your ideal VDC. Realistic VDC, it will be 0.7 volt lower for the half wave rectifier where you have one diode drop. For bridge rectifier, you have 0.636 times Vm minus 2 times 0.7 volts. So because there are two diode drops in a bridge rectifier, you have to subtract 1.4 volts from whatever DC that you create. For a center tap transformer rectifier, you have only one diode drop. So that is the reason why for a realistic scenario, assuming that the transformer is ideal, the center tap transformer gives you a higher amount of DC voltage. All right, now let's come to clippers and clampers. So you are asking a question about clippers, right? So the clipper circuit is defined as something that clips off part of the voltage, and it uses a reverse bias diode to create that clipped voltage. So for example, in this circuit, what you see on the top right, you have a diode and then you have a resistor across which you're taking the output voltage, and your input voltage is on the left side. So this diode is called a series clipper circuit. It clips any voltage that does not forward bias it, because as soon as the diode is reverse biased, the voltage, you see the diode becomes open circuited. So the entire voltage drop will happen across the diode and nothing will reach the resistor. So if you have your input that looks like this square wave, what you'll see at the output is just the positive half cycle of the square wave. This is a triangular wave. Again, you'll see only the negative, or only the positive half cycle of the triangular wave. So in circuits where you do not want the negative polarity to affect your output, for example, let's say some kind of a surge protection circuit, you can use the diode clipper. Now you can also bias the clippers. For example, this is an interesting scenario, interesting example, where you have put a battery in series with the diode. So what does this mean? This means that, and look at the polarity of the battery. The polarity of the battery is such that your negative terminal of the battery is on the left, the positive terminal is on the right. So as you're applying this input voltage, and this input voltage looks like this sine wave once again. Okay. So let's say you apply your peak is at 20 volt, and assuming that the diode can withstand 20 volt. So when you have 20 volt over here, and then you have a battery with the negative terminal and the positive terminal as indicated, how much does your diode see? The diode will see 25 volt total, right? So of course the diode will be forward biased. And you'll see that voltage across this resistor. However, when the input voltage is minus 5 volt, or minus 4 volt, or minus 3 volts, even in that case, because you're adding this 5 volt with whatever your input is. So if your input is minus 5, minus 4, minus 3 volts, you just add 5 volt to it because the 5 volt is coming in series, right? So if you have a minus 3 volt as your input, you add 5 volt to it, the diode will see plus 2 volts. So the diode will still be forward biased when your input is minus 5 volt. So how would you represent this graphically? That again, you have this 20 volt peak to 20 volt peak or 40 volt peak to peak sine wave. You draw this line at minus 5 volt. Right? Whatever is above minus 5 volt will pass through the diode. Okay? So the signal that gets passed through the diode looks like this. The peak is at 5 volt plus 20 volt. So the peak is at 25 volt. The midpoint of the sine wave, the original midpoint of the sine wave, now is at 5 volt. And then you are passing what was there originally in the sine wave from 0 to minus 5 volt. That those voltages are also getting passed through the diode. So this is what you get when you apply a battery in the direction that it is shown here in this particular diagram. So this is called a bias clipper because you are biasing the clippered circuit with a battery to go in a positive or negative direction. If you had applied the battery in the opposite direction with the opposite polarity, you would have clipped the signal over here. And only the part which is above the plus 5 volt, that will be passed if the battery was in the opposite direction, connected in the opposite direction. How does a parallel clipper circuit look like? By definition, the parallel clipper is a circuit where the diode comes in the parallel path. Right? So you have the resistance in the series path, and then if this is a ground, then you have this diode going to ground or the negative terminal. So the diode comes in the path which is shunting the signal to ground. So the parallel clipper circuit will clip any voltage that will forward bias it. What does this mean? Let's take a look that if you have a sine wave, again at the input side, whenever the sine wave has the positive half cycle, the diode is forward bias. If the diode is ideal, it will have a voltage drop of 0 across it, right? And all the voltage drop will happen across the resistor. But because you're taking your output across the diode, when your input is in the positive half cycle, the diode voltage or the voltage across the diode is 0 volt because the diode is forward bias. So that is the difference between the series clipper and the parallel clipper. That in the series clipper case, when the diode is forward biased, you will see signal at the output. In a parallel clipper scenario, if the diode is forward biased, you'll not see anything at the output because the output is taken across the diode. So if the diode is forward biased, it is shorted and the voltage across a short circuit is 0. So in this case, square wave, again, the positive half cycle is clipped off. Triangular wave, positive half cycle is clipped off. Only the negative half cycle remains. Okay, so if you want to take a summary of these series, the clipper circuits. So simple series clipper, you can have positive clippers or negative clippers, and that will depend on the direction of the diode. So you see from between these two diagrams, in the left and the right on the top half, the only difference is that the direction of the diode is interchanged. For the positive series clipper, again, you don't need to remember the names, but by looking at the circuit, you should be able to say how the output of the circuit looks like. Okay. So for the positive clipper circuit, what you have here is the diode facing toward the left side. So the diode will only conduct in this direction. That means the diode can only conduct in the negative half cycle. It cannot even conduct anything in the positive half cycle, when this will become plus and this will become minus. Right? The diode does not conduct anything in that scenario, but in the negative half cycle, the diode conducts. If you reverse the direction of the diode, or basically the P and N terminals of the diode, you have a negative clipper. That means you're clipping off the negative half cycle. So the name comes from what you are clipping off. Positive clipper means the positive half cycle is clipped off. Negative clipper means the negative half cycle is clipped off. Okay. You can also have these biased clippers with ideal diodes. If the diode is non-ideal, add that 0.7 volt with the bias that you're adding. Okay. So if you have a voltage connected like, or if you have a battery connected like this versus that, okay, what would happen in case of the series clipper in the positive scenario? So again, you can do the calculation in a graphical manner. You can do the calculation using numbers. But what you end up with is that when the diode conducts, do I add a voltage or do I subtract a voltage from it? Right. So for example, when this diode conducts, right? So that means the positive is in this side, the negative is in this side, which will only happen in the negative half cycle. But in that case, you have the battery connected with the negative side here and the positive side on the left side, which means that you're adding the voltages in series. And in that case, your output voltage will look like this, that you are biasing the clipper, but you get more than half the cycle because you had this bias battery working in a way that more than half of the cycle passed through the diode. Similarly, if you reverse the polarity of the battery, then less than half of the cycle will pass through the diode. And same thing you can do for the negative clipper circuit as well. And we already saw this example earlier, that with the negative clipper circuit, if you have this battery connected in this manner, so this is minus, this is plus, and of course you're applying the input here plus and minus. So which means that you're adding this series battery in series, which means that you will pass more than half of the cycle. And in the opposite scenario, when the polarity of that battery is reversed, you'll pass less than half of the cycle. Questions?
Do these clipper circuits assume that you have like a very small load attached to them because like the resistor explode up like this?
That's a good question. So the very small load means very small amount of current flowing through it. So of course the diode will have a maximum amount of current that it can pass through. So very small load means very large resistance. So you can assume, of course, whenever you're building any circuit, you have to assume that it's realistic, it's practical, and the diode does not burn or the resistor does not burn. So those kind of things you always have to keep in mind, which really means what you said is correct, that the load or the current should be very small, or at least smaller than what the diode and resistor can handle. Yeah. Okay, similarly, you can again do the calculations for parallel clipper circuits. And remember that the parallel clipper circuit, for that, the diode will be connected in shunt, in parallel, and you are taking the output voltage across the diode. So simple parallel clipper with ideal diode, they will conduct only in the negative half cycle, because only in the negative half cycle the diode is reverse biased, and only if the diode is reverse biased you get a voltage across them. If the diode is forward biased, the diode is a short circuit and the voltage across a short circuit is zero. So you clip off the positive half cycle. On the other hand, in this scenario, you clip off the negative half cycle, so you get a positive half cycle only. Just like we did biased series clippers, you can have biased parallel clippers that along with the diode, you can put a battery in the parallel path as well, right? So for example, let's take a look at the first scenario over here. So you have a battery in a direction that when the diode conducts like this, it will also see a additional voltage over here, V amount of voltage. If this is an ideal diode, the diode will start conducting as soon as it gets a gets any voltage a little higher than 0. So let's say you have 0.1 volt. So if you have 0.1 volt at the input, the diode will start conducting. Of course, you have this voltage V connected, and what that will mean is that if you have a voltage V or below a voltage V, the diode will conduct. Okay? So if the voltage V, let's say this is 1 volt, so anything below plus 1 volt for the sine wave, it will conduct. In the previous scenario, without the bias condition, the diode would have conducted, or basically you'll see output voltage when your input is below 0 volt. In this case, you'll see output voltage when your input is below 1 volt. Because as soon as your input goes below 1 volt, the diode becomes reverse biased. And you'll only have an output if the diode is reverse biased. Similarly, you can find out what would happen in this scenario when the polarity of the battery is reversed. And you can just do the math. Basically, you can just do a line at minus V, and you'll know that and you can understand that which part will conduct out of the two. Now, this is something interesting. Here you have two diodes, one connected in this direction, the other is connected in this direction. And you have two batteries, let's say 1 volt or 0.7 volt here, and you have, let's say, minus 0.7 volt here. So what would this circuit do? Interestingly, this circuit will clip off the top part of the sine wave and the bottom part of the sine. Why? Because when this diode is conducting, when does that happen? That happens only in the positive half cycle, right? And if the input voltage is more than, if the input voltage is more than V1, if the input voltage is more than V1, then the diode will be forward biased. If the diode is forward biased, the voltage drop across the diode will be 0. So the only voltage drop that you see from this point to that point is going to be equal to V1. Okay? So if the input voltage is more than V1, this point's voltage will be more than V1, whereas this point's voltage will be exactly equal to V1. That means the diode will be forward biased. If the diode is forward biased, the voltage drop across the diode is 0. So the total voltage drop from the top terminal to the bottom terminal is going to be equal to V1. Okay? If the input voltage is less than V1, in that case, you will have the diode reverse biased, and the voltage drop across the diode will be same as, or basically if the input voltage is over here, which is equal to V1, that will be the same voltage that you see between these two terminals. So when the input voltage is less than V1 but more than 0, then this part is activated, and you see the voltage across the diode and the battery structure as what you see on the right side. Similarly, the reverse will happen for this part, that when the input voltage is negative in the negative half cycle, and if it is less than minus V2, if the input voltage is in the negative half cycle and less than minus V2, in that case, this diode will turn on, it will be in the forward bias, and it will limit the voltage drop across the positive terminal and negative terminal as minus V2. Because the diode is a short, what you see is only the battery voltage, which is minus V2 in this case. So why is this circuit important? You may have heard something about the ESD protection circuitry for any electronic circuit. So ESD stands for electrostatic discharge, and electrostatic discharge can happen from anywhere. For example, my body can store voltages up to thousands of volts. And you can see this in any ESD protection circuits document, that they are going to protect the circuit till, let's say, 3000 volts or so. That is because if I accidentally touch that electronic component, I can damage it because my body has a very high amount of charge or very high amount of voltage. The current is very small because I'm not conducting as much, but the voltage that I'm storing could be very high. And it can instantaneously get passed through the electronic circuit and damage it. And that is the reason why electrostatic discharge or ESD protection circuits are required. These are also called surge protection circuits sometimes. And what you'll see is that that will be designed using these two back-to-back diodes, something like this. You may or may not have biasing in the electrostatic discharge protection or the ESD protection circuit. You may choose to have biasing. In that case, you have to choose a battery or a cell that you can connect to it. But remember that any diode will have a threshold voltage, right? So that battery is already connected with a real diode. With an ideal diode, you have to connect the battery. But with a real diode, that battery is already connected, and the value of that battery, the voltage in that battery is 0.7 volt, which is a threshold voltage of the diode. So you can create this kind of a clipping circuitry that any voltage above 0.7 volt or above, let's say you bias it to, let's say, plus 5 volt and minus 5 volt. So above plus 5 volt or below minus 5 volt, everything else will be cut off, so that your original circuit does not see the high voltage. So a ESD protection circuit will look like this, that you can design using two back-to-back diodes. And any circuit that you design, let's say you're designing a chip in TI or Apple or Intel and so on, they will always have these ESD protection circuitry, specifically at the pads of the chip. So the chip will have multiple pads through which you communicate with the outside world. And because you communicate with the outside world, there is a chance that the outside world will also try to force a very high amount of voltage to it, unknowingly or unintentionally. So that can be protected by using these two back-to-back diodes in all the pads of a chip. So that is one very real application of diodes within an electronic chip. And the same circuit used in every chip in Intel, Apple, Qualcomm, TI, Youngblood devices, whatever you say, this same circuit is used everywhere. All right. So this is again just the last part of the clipper circuit summary, that if you had the series clipper circuit, now you put the diode back to the series path, and then you can create these different types of biasing, and then how would it look like? All right. The last thing that I want to talk about very quickly, maybe in the next 1 minute or so, is clamper circuits. A diode and a capacitor is called a clamper. So just like a clipper, you also can create a clamper circuit. And the job of the clamper is to clamp an AC signal to a specific DC level. So let's say originally you had this AC signal. Now you want to push this entire AC signal down. If you push this entire AC signal down, let's say the average value, you do not want to clip it. So see, in this case, you are not clipping it. You are moving the entire AC signal up and down. In the previous scenario with the clipper circuits, you are getting rid of part of the signal. But how you can move the entire signal up and down is that you pass it through a capacitor, and then you have basically a diode and a resistor in parallel. What that will do is that the AC will get passed through the capacitor, of course. And let's look at the next slide to see. Okay. So let's just analyze it here. So basically, you have your AC signal that is passing through the capacitor, and then the diode will conduct in this direction only if it sees a positive voltage here. So if you have this positive voltage, the diode will conduct, and if you have the negative voltage, the diode will not conduct. But because you have stored you are passing through the capacitor, you're also storing the voltage, the input voltage at the capacitor. Because you are storing the input voltage of the capacitor, maybe we can take this in the next lecture because I want to show this in a little bit more detail, but think about it, that because you're storing the input voltage at the capacitor, the next time the diode turns on, it sees a different voltage as compared to the input, because there is a version of the input already stored on the capacitor. So I'll go through the entire, not the derivation, but how to analyze this circuit in the beginning of the next lecture, and then we'll start with MOSFETs. Okay, but the BJT-based circuits and the analysis, please look at the self-study section. We'll come back to BJTs after we discuss MOSFETs in the course. But if you're interested, please look into the BJTs as well. One last announcement is that this week there are no labs because of the career fair. So all the best. Talk to whichever companies you are interested in. We'll start with the labs next week. But what that also means is that you get 1 extra week to submit the in-lab section for lab number 2. So please submit it by this week if you haven't submitted it already.